Hello and welcome to my video, lesson 7.3 on radioactive decay. So regardless of the type of radioactive decay, it must follow the normal four conservation laws, so conservation of momentum, mass, energy, charge, and conservation of nucleons, i.e. mass number. There are multiple types of decay we're going to look at, alpha, beta, and gamma. And beta has beta positive and beta negative decay. And so we're just going to look at these one at a time. So for alpha decay, basically what's happening is that the parent nucleus, the original nucleus, loses an alpha particle worth of matter, which is written like this or sometimes written like this, because a helium atom without the electrons is an alpha particle. So there's no electrons on here, but it's losing that helium atom. And alpha decay, like we said, it can be very dangerous, but goes short distances because it's a whole atom. It's pretty heavy. It's pretty big, relatively speaking. Okay, so we just we subtract the mass number and we subtract the proton number, and we get our new element. Beta negative decay is interesting because what happens is that a neutron turns into a proton. So that sounds like it should become beta positive because it turns into a proton, but what actually is happening is it's shooting off an electron. This is the other way we could write it, but we call a beta particle or beta negative particle, which is just an electron. And so a neutron turns into a proton, and when it does that, it shoots off an electron so that the charges still line up with what they were before. So before it was neutral, and after it was a +1 and a -1. And +1 and -1 together are neutral. So the charges are now conserved, and this is important. Okay? Now, why is there an antineutrino here? Well, what happens is when you convert from a neutron to a proton, we actually have more mass here and just slightly less mass here. I mean, it's very, very similar, but it's less mass here. Actually, let's not talk about it as more mass, less mass. Let's just say there is a mass difference, and so this kind of makes up the difference in the two situations. And yeah, we'll just leave it at that, okay? I know that's not super clear, but we'll just leave it there. For the purposes of Physics 30, all you have to know is that it will be shooting this antineutrino with a beta negative decay. Beta positive is the opposite of this. So here, let's just talk about the charges first. The charges are most important. So it's +1, and then afterwards it's 0 because it's a neutron, but it's also plus a positron, so plus a +1. So it still is the same charge before and after. And then we've got a proton turning into a neutron, and we're also shooting off the neutrino, which apparently makes the masses work, but is not entirely clear to me how. So yeah, anyways, it's important because it helps us obey the laws of conservation, conservation of momentum and mass and such. Okay? And then a gamma decay doesn't actually change the parent nucleus at all, because we're starting with whatever it is, and we're entering with the same thing. We haven't changed the nucleus, the proton number, the neutron number at all. All we're doing is we're shooting off a high energy gamma ray. So it's just simply a lot of extra energy, and it just gets emitted. It often happens after alpha or beta decay. Okay, so we have 3 questions here. I recommend you pause the video now and try them yourself and see if you get the same answer as me. Alright, so iodine 131, that's the mass number, decays into xenon 131. Now, what we need to do is we need to check the proton number. So iodine, if you look in your formula sheet, is 53. Xenon is 54. So what that means is that one of our neutrons has turned into a proton because our total mass number hasn't changed, but the proton count has gone up by 1. So that means we've gained a proton, which means to balance it out, we must be shooting off an electron or a beta negative or an electron. Either way you want to say it is fine. Okay, so either way is fine. But we're shooting off an electron, and if it's an electron we're shooting off, then it's also an antineutrino. So this is called beta negative decay. All right, and there's the formula for it. You should get used to trying to write the formula out properly. So pause the video now and try the next one and see if you get the same answer as me. Uranium-235, so again, uranium-235 ends up here. Then you check your formula sheet and we get 92 is the proton count. Undergoes an alpha particle decay. So I'm going to write it like this as helium 2,4. So basically, we're going to use those numbers to subtract from these numbers. So it's 90 and 231. So which element has 90? Well, it is thorium. TH, thorium. And this is alpha particle decay. So what is the daughter atom? Well, it's thorium 231. All right, and for our last example, a beta positive decay occurs, and the result is boron 10. What was the parent nucleus? So now we're going to go like this and say that there's a beta positive, which means that there's a regular neutrino shooting off, and the result is boron 10. Boron has a 5 here. So beta positive means so we've added this positron here. That's what that beta positive means, which means that to have the count remain the same, we should have a 6 over here, a 10 here. So it must have been carbon 10 originally. So what was the parent nucleus? It was carbon 10. Okay, and maybe what you might notice is things that decay are usually because the number is not matching what is commonly found in nature. So it's not matching the stable state. So if you look on your formula sheet, the closest number that carbon has is carbon 12. That's the most abundant type. That is the stable form. So if it's not carbon 12, it's probably decaying. Carbon 14, carbon 13, carbon 10, right? Iodine is 127, but we have 131, which is why we have an issue. Okay, uranium is 238, so when we have 235, it's an issue. All right, and usually they decay into a more stable nucleus or atom, and then they might continue to decay after that even. Alright, so these are all the different types of decay. I hope this video helped you better understand radioactive decay and some examples. Good luck!